So you stumbled upon this video, and now you're looking at the title card, and now you're reading the description, and you're thinking, what exactly is a vector derivative? They didn't tell me about this? Well, it turns out that you can extend normal derivatives from the scalar field onto other more complicated fields, like the vector field. You can also take derivatives of matrices and higher dimensional matrix-like objects called tensors, but we're not going to cover that today. Today we're going to keep it to the basics of vector derivatives. And the most basic you can get is taking the derivative of x, of course. At the top you can see that I've written the derivative of x, and that's in the scalar field. You can see to the right I've written x is in the real field. That's what that little icon means. And we've decided that the derivative of x is 1. Well, with vector derivatives, it's actually very similar. But instead of 1, we're going to use the identity matrix. Because, if you'll notice, we're not operating with plain old numbers anymore. We're operating with vectors and matrices. And with vectors and matrices, the identity matrix tends to stand in for where we would usually use 1 in the scalar field. But if you're confused, I'll show you exactly why this is true in a bit. And similarly to the derivative of x being the identity matrix, if you just take the derivative with respect to, say, the first element of x, x naught, then you get the first column of the identity matrix. Similarly, if you take the derivative with respect to x, the vector, of just the first element of x, then you get the first row of the identity matrix. Interesting. First off, why does deriving with respect to x naught give a column of I? This will help us understand the whole I picture. The first thing to note is that derivatives are linear. So that means that you can apply them inside the individual items of the vector. And then, well, looks like our work is done for us. We can just apply the normal scalar derivative rules and we have what looks like the first column of I. And it's worth noting that this generalizes to all the columns of I. So I'll just take a moment to go through and update these less than general formulas. Now, extending to I is actually pretty easy. We have to note our result for the columns of I, and then we can just separate out our derivative of x into the corresponding columns of the derivative of x. And then you can just note that each column is just a column of I. And so putting all the columns together, we can see that the output is just I. I've shown 2 out of the 3 identities for producing I, or rows of I, or columns of I, but the third I can leave as an exercise. It's pretty simple to show. Okay, I've shown the simplest derivative, but now we have to get into the meat and potatoes of vector derivatives. So the closest analog to what I'm about to do is the scalar derivative of ax, where a is a constant, and we're taking the derivative with respect to x. Lo and behold, the same exists for vector derivatives. If you have ax, and a is a scalar constant, and x is what you're deriving over, then we can pull the a out of the derivative, and we get ai. Now if A is a matrix on the other hand, well, we can actually pull that one out of the derivative as well, and we still get AI. And this is a pretty interesting result because A shuffles all of the elements of X, but we're about to see why the derivative works out this way. To see this, I'm going to break down a times x into a series of dot products specifically dotting the rows of A with all of X. And you can see that each entry in the output is exactly the dot product of row I of A and X. Now that we have a bunch of dot products, I want to see what exactly is the derivative of a dot product. And specifically, I'm going to do this by element of X. So here I'm going to do it by X naught. But I'm going to expand the dot product into the sum that it really is, and then we can see the derivative is just going to be the derivative of the first term in the sum, because that's the only one that contains X naught. And so if we apply this derivative element-wise across the whole vector, we can see the result is just going to be y transpose. The transpose is hard to see, but it's going to allow things like the chain rule to work as we expect. Anyway, we can apply this new derivative we just learned to the dots between the rows of A and X. And we can see that the result we get is in fact A. Now I think I'll just go back and update the full list of formulas that we've explored today. And that's pretty much it. That's the introduction to the basic rules of vector calculus. Of course, there are many, many more identities that are important to know, and hopefully I'll have time to cover them in the future. But these are the real cornerstones, and they're the ones that you can build all the other ones off of. Anyway, thank you so much for watching. Hope you learned something new.